Okay. Hello, everyone. My name is Jess Williams. I am an incoming first-year student at the London School of Economics and Political Science. I graduated Plano Senior High in 2020, a year early because of COVID, and I'm going to be studying BSc in Mathematics and Economics. And this is essentially, the purpose of this is really more so a model to show or to really refurbish the Eliza Mills model, because of the fact that it's making a few assumptions that aren't necessarily going to be holding now in the age of remote work. And this is motivated by the fact that a recent survey of business economists stated that about 40% of the people who are currently remote working will be doing so permanently, and we need to hence revise our urban models effectively to make sure that they're still modeling what we want them to model. And in this case, I'll be refurbishing the AMM model, or the Eliza Mills model, which is the simplest model you can possibly imagine for a monocentric city. And that's the other qualifications I have. I'm an AJAS fellow for a research project I did looking at how the Fibonacci sequence pertains to equity markets. And I've done several things in terms of like personal finance and econ competitions on like national level, but you can look at my LinkedIn for that if you want more information. Anyway, so to start this presentation, so the idea of what we're doing today is that I want to first give you an introduction to the field of urban economics and how that differs particularly from things like economic geography. And then looking specifically at the city in the age of COVID, right? What will change from before? And then lastly, what I was just discussing, which is going to be the refurbishment of the Eliza Mills model. So first, why do people even organize in cities? And that's because, ever since this transition from the Paleolithic era to the Neolithic era in about 4500 BC, there's been a distinct benefit to organize next to other humans. And this becomes, it's a division of labor idea, the idea of economics of specialization. And essentially, as we get, as we live together and as more people live in one area, we can begin to specialize with what we're better at doing, right? So you do whatever you have the lower opportunity costs in doing in comparison to someone else. Whether that be produce food in the village, that would be the case. Whether that would be to go build wheels or carts or whatever, that would also be the case. So you have this economics of specialization that sort of shows what the benefits of cities are. And if you look at Adam Smith regarding cities, there are some sorts of industry, even of the lowest kind, which can be carried out nowhere but in a great town. A porter, for example, can find employment and subsistence in no other place. Or in the lone houses in very small villages, which are scattered about in so desert a country as the Highlands of Scotland, every farmer must be butcher, baker, and brewer for his own family. So this shows you that in the absence of cities, without cities, you'd have to do all these different tasks individually by yourself. So if you need bread, you'd have to grow the wheat and then bake the put it into, I don't know how to bake bread, but you get the point. And whereas if you have cities, you can specialize in each of these individual tasks, and you're better off because of that, right? And that's really the idea of why humans are going to organize themselves in the cities. So I think that's it for this slide. And an overview of urban economics, and this I pulled this from Ed Glazer's presentation on some of this. And basically, the idea of urban economics is it's a study of location of economic activity over space, which may sound like geography, but it really is urban economics because of the fact that you're looking at different things such as wages and housing costs, which really is better suited for an economic discipline rather than geography. And you're really focusing on why things are located where they are. So, if you're located next to a factory, for instance, the shop is close to the factory, that's going to reduce transportation costs. And this is not just for goods and people, but also for ideas. So a distinctive example of that is car manufacturing, right? So an instance I jumps to my mind is Fuyao, a glass corporation. It's a Chinese company, which is now directly investing in the United States by building a factory that went out of business from Ford or General Motors days. And essentially it's trying to produce things such as glass that's on like your windshield or on the car windows that sort of allows that's going to sort of allow you to so its proximity to the factories in Detroit is why that you're going to bring those jobs to America rather than have them in China, because the closeness of the agglomeration economies sort of is going to outweigh any benefit that you're going to have from lower costs of production, especially with labor costs in a place such as China. And this sort of goes with the idea of agglomeration economies. So if you have a city, one of the reasons that people are going to sort of go together in a city or cluster together is because that if you're closer geographically to other people, other firms, your factories and the shops, then your transportation costs are going to be lower, which therefore is how that would make sense. And you also have things such as things like human capital externalities, and this is really that being around smart people is going to make you smarter. So this is particularly the case. This is sort of what distinguishes cities such as Seattle and Detroit, right? Both of them in the 1970s were having major issues in terms of manufacturing and in terms of the companies that were employing a vast number of people in each one of those cities, particularly Boeing for Seattle and GM and Ford for Detroit. And what made Seattle prosperous in the long run, and what made Detroit not so prosperous, is the fact that Seattle had a much higher level of human capital, right? So you had great universities, you had a very highly educated city with Microsoft and with Boeing, whereas in Detroit you had these huge manufacturing firms manufacturing automobiles, and they were not nearly as well off in terms of human capital. So this idea that being closer to smart people makes you smarter is actually something that can be empirically measured, and the results do show that empirically. And this does not just apply to urban areas, but this idea of density, proximity, closeness also applies to things such as college campuses. This is one of the reasons why Facebook was even started at Harvard, because of the fact that you had Zuckerberg in close proximity to the financial ideas of Eduardo, and the social networking ideas of the Winklevoss twins, and obviously you had the whole ensuing lawsuit. But the idea that Zuckerberg was able to get ideas from other people, from other smart people in terms of social networking is what gave him the idea for Facebook, and it's why we have such widespread social media and social networks today. So those are just a few examples. You also have this idea of neighborhood effects, right? So that some people in certain neighborhoods, the neighborhood that you live in is going to have different levels of human capital, and that's going to obviously influence outcomes in terms of upward mobility. Rod Shetty has done some very interesting research on this in terms of like the 40 people that are surrounding you or something are going to have huge impacts on your upward mobility. And this also has great implications in the field of network economics as well, where like if you're if something is a relative complement and you're given network, then you're more likely to take up that behavior, such as if you're in a very terrible community where you have high drug usage, if your peers are doing drugs, you're more likely to as well. If your peers are drinking excessively, such as in like an Irish ghetto, you're more likely to have that behavior as well. And most fundamentally, and we'll see this in our model as well, is that what determines price is the price that people are willing to pay to live in a particular place. So this is why real estate economics is a close cousin to urban economics, because urban economics is where you are in a given city, in a given spatial equilibrium, is going to determine the price you pay for housing. And that is so crucial in terms of what we're doing here. I think that's it for now. Okay, in terms of nefarious policy, and there are two main types of nefarious policy that we see policymakers engaging in, and that is going to be the ideas of NIMBYism and monumentalism. And NIMBYism is sort of this idea of not in my backyard, and you add the ism to the end for flair. So think Greenwich Village in New York or Paris, and these cities are cities where it's fundamentally terribly hard to build. Right. So, and in some of these cities, such as Paris or Venice or Bruges, that can be very well justified, right? Because, Venice, it should be hard to build because Venice is a major tourist draw for the country of Italy and a major part of its economy. But, you have cases such as, those in Greenwich Village where that might not necessarily be the case, right? I mean, we should not need to preserve every single, red brick building. And, because of this idea of NIMBYism, you're going to have higher housing costs because of, an inability to build up or things such as that. And, this is one of the areas of Jane Jacobs' points of view, perspectives that was actually wrong. Because, the NIMBYism perspective would argue that, you should not be building up because you want to maintain the, original climate of a certain neighborhood, which is going to be a flawed idea because building up does substantially reduce housing costs and makes the city more accessible for all. The other idea is probably a less common one, and it's called monumentalism. And this is basically building infrastructure in places where there isn't really a city, or building infrastructure in the absence of people. And this sort of, the issue of this idea is that you must remember that the cities fundamentally are people. The people who compose the city are the city, not the architecture, the buildings they live in. So, if you're dealing with troubling instances or, times of great despair in a certain city, such as Detroit after the 1967 race riots, which was partially propagated by Dennis Coleman, and, these policies to, start building, where basically Dennis Coleman and several other Detroit mayors just started building, engaging in these massive infrastructure projects, such as, the Detroit People Mover, and ignoring the fundamental idea that, if you have, massive immigration or migration from a given city, that, building certain infrastructure is not going to help your cause. That is one of the ideas of, why Detroit, or one of the ideas of policy failure of Detroit that is, probably still not probably harmed it today. Probably the most, I don't know about the most famous, but, a glaring example to me of monumentalism is Pyongyang, North Korea, where, Kim Jong-un has constructed these massive skyscrapers that practically no one lives in, which is, China does this as well. So, essentially you can think of these ideas as NIMBYism being almost too little space and monumentalism being too much space. And the last example of nefarious policy is going to be rent control. And rent control is horrible because of the fact that you're going to be, it's horrible because of the fact that initially it sounds like a great idea, right? We're going to limit the costs of apartments for certain groups, and we won't let it go up, and it will be this great marvelous thing, and poor people won't have to pay as much for housing, and that idea is deeply flawed. And the reason that is because of the fact that you have to think about who is getting the rent controlled housing, and also who is what is the effect on the rest of the market. So in terms of who is getting the rent-controlled housing, in New York, the 1999 study done by Eglazer basically stated that there's about a $500 million misallocation of housing in New York City because of rent control. And rent control, the idea is that essentially you're going to fix someone's rents who are already living in that housing. So essentially that their rents don't go up or go up a very limited amount. And I think this idea of rent control was originally established in New York City around the 1920s or 1940s, I forget when. But the issue is that it's still there today, which also shows you the implications of expansions of governmental power. Hi, James. So basically, you have this idea of rent control, and there's this idea of that, this negative effect of driving up housing costs for everyone else is going to outweigh any benefit it might provide to people who are in the rent controlled housing. So that's basically the idea of that. You can look at a derivation of that, using quasi-linear demand curves or quasi-linear supply curves in this case, I believe, since it's the supply of housing, on the Ec 1011A course videos site that Glacier has done. But that's essentially the main idea of why it's an issue. And by the way, I do apologize if any of these explanations aren't up to your satisfaction. I've mainly been trying to focus on the mathematics, which is still to come. You may excoriate me in the comment section if you so wish. And also later, I apologize if there are any algebraic errors or any issues in intuition. I spent probably about 20 hours on this, so some of this is quite arduous. Okay, so now we're sort of into the part of the presentation about cities and disease. And cities throughout history have had an interesting relationship with disease, in that the initial effects of the disease are almost always negative for cities, right? It prohibited Justinian from reimposing the Pax Romana due to the plague of Justinian from 541 to 549 CE. You also have, cases of the Black Death, which plagued southern Europe, particularly Italy, in the 14th century. And that led to the prominence of people such as the Hanseatic League in Northern Europe in the 12th or 13th to the 15th centuries. But we also should remember is that plague, the actual effects of plague aren't always terrible. And this is mainly depicted in the fact that the Black Death actually increased the prosperity for those people living in the areas affected by it afterwards, because of the fact that in Middle Age Europe and medieval Europe, most of your wealth came from subsistence agriculture, right? How much could you grow yourself? And that was highly dependent based on land size, right? So the bigger the amount of land you have, the more crops you could grow, and therefore the higher your level of well-being would be. And that was, the case after the Black Death. And I feel, and this was actually in my personal statement for the LSC about 10 months ago, or about a year ago, when I was writing it, and I was sort of thinking about, what would the effects be of, the COVID pandemic on the actual city. And my general theory was that we're going to see negative short-term effects, right? And that was obvious, right? People were dying. People were trying to de-urbanize because interacting with other people was becoming a sense of peril rather than a sense of pleasure. And because of this, you saw a drastic de-urbanization that we haven't seen in over a century in this country. And now with the emergence of being able to work from home, sure, you're going to see less people in cities, most likely. But this is not necessarily a bad thing, right? Because what's going to happen is that before, all of the housing is going to be unoccupied, such as in Detroit, you're going to have lowered housing costs. You're going to have lowered costs. And therefore, that's going to enable people who perhaps may have been priced out of places such as New York and San Francisco previously to now be able to afford real estate in these urban areas. And that could very well increase well-being and utility for those individuals. So that's just sort of something to think about, that despite this being horrible, it may not necessarily be terrible. Now, this is all under the assumption that that we will recover from the COVID-19 pandemic, which looks to be rather likely right now because of the the effectiveness of the vaccine and the spread of the Delta variant being mainly among the unvaccinated. But if this does not occur, then sure, cities are going to have a very rough time because of the fact that interacting with people is going to be feeling a peril rather than a pleasure, and because in a given city, because of the fact that you have density, proximity, and closeness, you're going to be interacting with others at a higher frequency than you would if you were living in rural America. So I think that's basically all I have to say here. Okay, and that's it for now. So now we're going to get into the model. Okay, so the Alonzo Muth Mills model. And I don't know how long I've talked for so far, so this is probably going to be quite long, which is quite sad because I wanted this to be concise, but whatever. I do apologize. So the basics of the Alonzo Muth Mills model is that you have some sort of monocentric city. So you have a circular city. Now we can already see ideas and situations where this would be terribly flawed. Houston has multiple central business districts where people work, the Galleria, the downtown. Manhattan itself has 2 central business districts, right? The central business district, built around the port, and the central business district built around, those rail stations from, mid 20th century where people commute into the city. Anyways, so yes, monocentric city, it can be wrong. And when people were initially trying to model the city in the 1950s, there was sort of lots of debate over how to model a particular urban area. And because of this, we'll start here. We'll start with what the 1950s economists were doing and where they were running into issues. So just some basic variable definitions here. We'll say that utility function is going to be a utility function based on consumption, travel time, and living space, which we will sort of think of as land at this point. D is going to denote the distance from the city center. Travel time is going to be T of D, where T prime of D is positive. So as you increase the distance from the city center, your travel time is going to increase. Living space is going to be represented by H, which, I mean, you could assume H is equal to L. We might do that later. Wage is W, and hours worked is S. So quite a simple model here. And PH of D is going to be the price of a living space. So now we're going to define the particular budget set, which is just the wage times the amount you work, minus the price of housing times the housing, and that's going to be equal to your consumption. So a fairly simple budget set. And then we will take the derivative of that with, I'm sorry, yes. No, we won't. So we're going to try a welfare function here, which is going to be U of that consumption times comma the travel time and H. And then we're going to continue to assume that everything is going to be continuously differentiable. We'll assume that quite gleefully. And then we're going to maximize that utility function with respect to D. And we will assume that D is positive or equal to 0. And that leads you to your first order condition, which is going to be negative P H prime of D times H times the derivative of utility with respect to consumption plus T prime of D times the derivative of the utility function with respect to travel time, and that's going to be equal to 0 because it's just how you would generally do a first order condition in calculus. Let's see, should I denote anything here? Perhaps I should denote that this derivative comes from essentially multi, right? Because we have a multivariate function here of consumption, travel time, and living space. So if you're differentiating in terms of D, you're going to have to multiply. Essentially, how you're going to do it is that you're going to take the derivative of the overall function with respect to the variable that you're sort of you sort of have a derivation for. So that's going to be consumption in this case. So you're going to take the derivative of the utility function with respect to consumption, and then you have to take the derivative of this consumption thing with respect to whatever you're differentiating to. In this case, is going to be distance. So that's how you're going to get each one of these terms here. So this is going to be du dc. This is going to be negative p prime of hd times h, because it's going to be differentiated with respect to this distance here. And then the other thing that has dn is going to be travel time, and it's going to be the same argument there. So this result is going to be, okay. And then also going back here, this thing is going to give you this ratio here, that the derivative of that pH prime of D is going to be equal to T prime of D over H times the UDT over the UDC. And this basically shows you that the increase, or as you move away from the city center, that your housing costs should decline, which is nice and all, right? And we probably explain how we get that. The UDT, right, as you increase travel time, your utility should be diminishing or decreasing, right? It should be negative because you value travel time negatively. As you increase consumption, your utility is positive. So this term here is going to be negative. Then you have a T prime of D, which we assumed was positive. So you have a positive, the housing should be positive. A positive times a negative is going to get you a negative. So this just shows you that as you increase distance, your housing prices is going to fall. So it's fairly simple. But you're going to figure out that, like, you can't model a city using this equation, which is sort of the issue, because you want to. I mean, that's the whole idea of doing an urban model, is to be able to model the whole monocentric city. So we need to sort of revise this, and that's particularly what Alonso did. And what I'm going to do essentially later is I'm going to attempt to get this travel time variable out and put in an amenity variable. And the reason that I use Alonso, that I decided to do this with the Alonso-Muth-Mills model in the first place, rather than something like the Rosenbach model, which uses amenities as has amenities in there, is that the amenities are, the Rosen-Rosenbach model essentially assumes that the wage you get is dependent on where you live, which is going to be a false assumption in the particular case where you're working from home. And also the Rosenbach model is much more difficult to work with. And this is, the AMM model is already quite computationally arduous. And I don't want to do more derivatives than I have to. So model definitions for the AMM and for my model. Really, this is mostly going to be my model here. So Alonso's leap of genius was the time-based budget constraint. And the time-based budget constraint is popularized by people such as Alonso, popularized by Gary Becker in modeling the time cost of kids. And essentially, it's going to assume that S is going to be equal to 1 minus the time you spend commuting, which is an obviously wrong assumption, but it works, so we don't care. And yes, the time spent working is now equal to 1 minus T of D. And what I'm going to do, at least initially, because I'm going to have to change it eventually for algebraic reasons, but it's going to, the change is going to represent the exact same thing. I'm going to use a variation of sort of thinking about being able to rewrite this travel time variable, where in my case, it's amenities variable, because in my model, I'm essentially assuming that the initial derivation for the utility function is going to be U of consumption, amenities, and living space, rather than this travel time variable. Because fundamentally, in the age of COVID, if everyone is working from home, you're not going to be commuting to a city center, right? You're going to be living in that given area. So therefore, it would be rather foolish to think of travel time as being a major factor if everyone is working from home, which is the assumption that we're making here. So yes, I'm going to, instead of multiplying W by 1 minus T of D, I'm going to multiply it by this function A of D. And A of D is going to represent your amenities in that given city. So as distance goes up, amenities are going to go down. So A prime of D is going to be negative. That makes sense, because think about Dallas, for instance, right? At the center of the city, you have all these fun attractions and bars and restaurants, the Pearl Museum, the AAC, the place where JFK got shot, if we want to call that fun. Dallas is quite boring, isn't it? But essentially, you're going to have more amenities as you get closer into that city center. And I'm going to think of this in my own model as, I'm going to think of A of D being essentially related to how much you work. And I'm going to argue this is not a ludicrous assumption because of the fact that if you live in a high amenity area, you're most likely going to need more money much money or a greater budget set or greater level of income M to enjoy those amenities. So therefore, you should be working by the amount of amenity is in your area respective to distance. And it's going to work, which is more important as we this is sort of a similar assumption in terms of logic to the AMM assumption. I'd actually argue that it's less feasible, but you may think differently, and this is a part of things where I want you to provide me with constructive criticism in the comment section. So anyways, model a welfare function is going to be A of D times W minus PH of D, H, and H. So basically what you're going to realize here is that we were able to essentially get rid of that amenities variable and sort of rewrite that in as part of the consumption function. So really, we're looking at the base utility function is going to be the utility of consumption of housing and housing. Again, we're going to consume this continuously differentiable. And then we're going to have our first order conditions being negative P H prime of D times H times the UDC plus A prime of D times W times the UDC is equal to 0. If I move the negative P H prime of D times H over to the other side, I'm going to get A prime of D W is equal to P H prime of D times H. So this is essentially going to show that the change in the amenities, if you're the distance times your wage is going to be equivalent to the change in housing prices with respect to distance times the housing, times the overall amount of housing consumed. And again, this all assumes that this is continuously differentiable because we're economists and we have to make assumptions like that, or else the model will just fall apart very quickly. Second order conditions are what we also call sufficiency conditions, is that you must have the UCC, UHH being less than 0 each respectively, which essentially means that they're concave, right? So the utility I get from consuming an additional unit of labor is going to be less. I'm sorry, of consuming an additional unit of a good, for instance, with consumption, is going to be less than the previous one. So think of that this is like you're stuffing your face with cookies, and that each cookie that you eat is going to give you less additional utility than the previous one. So both of those can be negative, and also assuming that this pH squared UCC plus 2 UCH pH minus UHH can be positive. And this is just for something that we'll see down the line with the comparative static with respect to distance. So anyways, so we're going to start taking comparative statics, and we're going to basically ask the question, how does housing vary with respect to distance? So therefore, I'm going to differentiate first with respect to housing. I'm going to differentiate this function here with respect to housing. So I'm going to get a negative PhD du dc plus a du dh is equal to 0. And if you use the implicit function theorem, which is sort of a magical result in economics, it basically states that if you take the derivative of this thing sort of implicitly, so basically what you're going to do is you're going to differentiate with respect to housing, and then from there you're going to get an optimal value of housing, and you can differentiate that with respect to some sort of parameter, and then basically that's going to get you precisely how the optimal value of housing is going to change with the distance from the city center in this case. This is a rather difficult idea to prove. I particularly cannot do it. If you so wish, you may assiduously study the Wikipedia article on the implicit function theorem or the envelope theorem. Here, the implicit function theorem is what we're using. Or maybe look at something like Francesco Nava's slides for Econ 401 at the LSE, or perhaps Ed Glazier's mathematics review videos for Ec 1011A. In order to better understand this concept. But basically, that's essentially what we're doing here, just implicitly differentiating this function. And I'll go through it right now. So what we have here is that you have negative pH of D times use of C of this thing plus use of H of this thing is going to be equal to 0. We're going to plug in the optimal values of H, and we're going to note this is H star of D in each one of these cases. And again, this just comes from, our first order condition, where this should be a maximum or should be an optimal value. And then we're going to differentiate with respect to distance. This is going to be where we're going to really use the simplistic function theorem. And then you're going to have this messy derivative where essentially here I'm going to use product rule, where you have pH from D UC, which is this thing, minus pH of D times the derivative of this utility function with respect to consumption. And so it's going to be the second derivative of this, which I'm going to get by differentiating this with respect to distance. So it's going to start out by being, I'm going to keep the scalar out in front because this is just a scalar. It's going to stay there. I'm sorry. This is going to be from this is from the product rule, not that it's a scalar. This is from the product rule. So anyway, you're going to differentiate this thing with respect to C. So I'm going to have the UCC times the A prime of D minus, again, we're using product rule, pH prime of D H star. The other part of that, because this is going to be F prime G plus FG prime. It's going to be the minus pH of D times the derivative of the optimal housing value with respect to distance, minus the derivative here with respect to housing, which is just going to be times the scalar minus pH of D times UCH, since you're going to take the derivative of this thing and then make it with respect to H, times the H star dd. And then that's going to be the first part of this derivative. And the second part is you're going to have to differentiate this thing with respect to distance as well. So you're going to get a UHC times A prime of D W minus PH prime of D H star minus PH of D D H star DD plus a UHH DH star is DD is equal to 0. And then from there, you're just going to combine in terms of simplify. So essentially what you're going to do here is you're just going to group this, that you're going to group these two terms here because they're both multiplied by this DH star DD. So that's what you're going to do here. And then I'm going to have the case where I'm going to notice that this term and this term are the exact same. So I'm just going to put this as a UHC minus PhD UCC. And that's where I get this term here. And then eventually what you can do is that you can separate this term here. You can break this down into an A prime of D W minus a PH prime of D H star times this thing plus a where is this? Where did it go? Plus this UHC minus PhD UCC minus this PhD DH star over DD. And from there, essentially, I can multiply this out with respect to this. So I'll multiply the negative pH with respect to this term, and I'll combine it with this term. So I get this term here, and then I can just divide this whole thing, move this over to the other side, or move this over to the other side, and divide out by that whole thing. I'm going to get this here. So you have the derivative of the optimal housing H star with respect to distance is going to be equal to negative pH from D plus this stuff here over the negative pH squared UCC plus UCH pH minus UHH. And this thing here is in our second order conditions. So go back to our model definition here. We assume this is positive. That's where it shows up. So we're going to assume that this is positive. Usually this thing is going to be a Hicksian demand curve. And this is what you're going to generally have in terms of the spatial equilibrium. Spatial equilibrium is generally going to give you a Hicksian demand curve because of the fact that we're assuming that utilities should be constant wherever you live in a city. If consumers or if city dwellers are going to be homogeneous, that's a crucial assumption because it would be ludicrous. There would be lunacy to assume that people with different income levels are going to have similar utilities, and we're not assuming that in this case. We're assuming that the dwellers will be homogeneous because of that. But anyway, so we're going to have the price effect here. So as you change as you increase distance, you're going to have, the price of housing is going to fall with respect to that. So this is going to be positive. That should basically state that you should consume more housing with distance. And something that you should notice here is that this term here, right here, this A prime of D W minus P H prime of D times H star is going to cancel out. And the reason that is because of the first order condition. Because of this first order condition, we assume that A prime of D W is equal to P H prime of D H. That's going to be the same thing as this thing right here. So this is going to cancel out. This is going to be 0. You're left with a beautiful and simple equation that says that the optimal value of housing is going to change based off of this thing with respect to distance using this relationship here. We know this is positive because of the fact that, as you change, did I miss a prime there? Yeah, I did. So this would be a P prime. Okay, good catch. So basically, as you go away from the city center, the price of housing is going to fall. This thing's going to be positive. This is going to be positive from second order conditions. We know that the optimal value of housing is going to increase as you increase the distance from the city center, and that should be what you see in real life, right? In suburbia, people live in larger houses than they do in the middle of a city. And again, this is going to be a Hicksian. Because of everyone getting a constant utility U bar. And this also leads to the crucial result that in a city there really is no best place to live. And this is, I'm looking at some real estate agents recently just because of some weird things have been going on with the Case-Shiller home price index. And in many of the cases I've seen, this area, the area where I'm selling my houses is going to be the absolute best place to live because of this factor and this factor. And that's just absolutely false and misleading because of the fact of the spatial equilibrium model, which tells us that dwellers in a city should be getting a utility U bar, regardless of where they are in the city, because an increase of housing consumption is going to equally be offset by a decrease in amenities, or a decrease in or an increase in travel time if you're going with the original Alonzo-Muthfield model. So yes, okay. So now we're going to go on to we're going to start to look at oh wait, this is the wrong slide. Housing supply. So there are two ways you can get basically a housing supply. You can assume that H is equal to L, which is on occasion how it's taught, but I'm not going to do that because I think it's a bit simplistic. You can also basically write a supply curve for usable space, which is what I'll be doing here. And it's the same thing as in the AMM, as in the original AMM model. So there are definitions. You're going to have H, and your H is going to be supplied using land and capital. PL of D is going to be the price of land. It's going to be endogenous, so it's going to be dependent on the model. You're going to have a building height of H. You're going to have delta as a cost parameter, and you're going to assume that big H is going to be equal to H times L, which is essentially the height of your building times land. So think of sort of like stackable units, like your Legos or something. And then you're going to have the cost of height being equal to H to the delta times L, where delta is greater than 1. And why does delta have to be greater than 1? Well, you should have some sort of increasing cost or height, right? That's why you don't build to infinity. And if delta was less than 1, you're either going to not build at all, or you're going to build to infinity. So we're going to have the developers maximization problem here. And that's going to be, you're going to maximize as H is greater than or equal to 0 of this function, which is going to basically be the PH of D times H of L minus H to delta L minus PL of D times L. This is basically going to be like revenues minus costs. So think of the revenues being the price of housing that they can get for the amount of housing they build, which is going to be equal to this H times L. parameter minus h to the delta times L, which is going to be the cost for building up if they decide to do so. And then minus the price of land, which is the cost they'll incur for building something. Think of, possibly like a developer for building a home, for instance, is going to be solving this maximization problem. If we take first order conditions on this with respect to H, this is about the simplest first order condition imaginable. You're going to have pH of D times L minus delta H delta minus 1 times L. And so that's going to be equal to 0. And then the L's are just going to, you can just divide those out. And then you can get the pH of D is going to be equal to delta times H to delta minus 1, or H is equal to pH of D over delta to the power of 1 over delta minus 1. And this just implies that heights are going to fall from the center of the city as well. And that's because we assume that this delta is going to be positive. I'm sorry, this delta is going to be greater than 1. So if this delta is greater than 1, then this exponent here is going to be less than 1. So that's going to imply that you're going to have falling heights from the center of the city. Okay, price of land. So now we can basically plug in this optimal height that we saw for here. Let me show you where it is. Right here, we can plug this back in to this price of land equation, which was what we were dealing with. Sorry, I'm playing back and forth here. And then you're going to have this huge screwed up function. And essentially you can, via the zero profit condition, that essentially they won't be making any profit, which is what we often assume. You can basically solve for the optimal price of land. And you're just going to be doing this by essentially looking at these exponents here. So you're just really manipulating exponents. It's like an exercise in algebra 2. So pH of D is going to be to the power of delta minus 1 over delta minus 1 times this other pH of D to the 1 minus delta minus 1. And I can combine those. So this thing is going to be a pH of D to the delta over delta minus 1. And then so is this thing here. And then I'm just going to have these delta parameters down here are the exponents. So these are just going to be negative exponents. So delta to the negative 1 over delta minus 1 minus delta to the negative delta over delta minus 1. And then from there, that's you can easily get the price of land just through that derivation. And then a few more variable definitions here. We're going to say that PA is going to be the agricultural value of land, and D bar is going to be the edge of the city. So if we here we're basically just going to solve for the edge of the city. So basically, PA is going to be equal to PL of D bar. So that you're just going to plug in a D bar for all this, and that you can use this to basically solve for D bar, which is what you should be doing here when we start to close the model. So okay, so there are two ways you can possibly close a model. I'm only going to do one of them since this is long enough, and I only think one of them is really relevant in this case. There's a closed city model, which I'm not going to focus on, where essentially you're going to assume that you have a fixed population size, and you're basically going to solve for the distance of the city based on population size or something like that. Like I said, I didn't work it, so I'm not as familiar with it. But generally speaking, the reason I'm not focusing on this is because if you have the case where everyone can work from home, you're going to have very high mobility and very high levels of migration into and out of the city. So in my opinion, it'd be infeasible to have a closed off city. And for the open city model, you're not going to be looking at like all the other cities in the US. You're just going to be looking at a particular utility level, which we are going to know as U bar. If you're going to have a utility that's going to be if you can get a utility that's greater than U bar from a given city, you're going to do that, and you're going to move into a city. that can provide you with that utility. Okay, so this is a case where I need to redefine some things. Otherwise, it won't work for the open city model. So I'm going to redefine the amenities function as being k times amenities proportion, where k is going to be the maximum value of a of d, which is going to occur when d is equal to 0. So basically just the value of a of d when you're at the city center. You're going to see why I did that in a second. And a of d is some proportion that is going to lie between 0 and 1. So I'm going to have a redefined utility function. U is equal to k, or u is a function of k, a, d, w minus p to d, h, and that's going to be equal to u bar. So at the city center, when d is equal to 0, you're going to know that a of d is going to be 1 because that's when your amenities are going to be maxed at that particular city center. So then I'm going to do the utility is going to be kw minus ph of 0 times h star of 0. That's going to be, then you also have another h star of 0, and that's going to be equal u bar. And the reason that we could get rid of this AD here is because of the fact that we assumed that this is a proportion that's going to lie between 0 and 1, and at the center it's going to be equal 1. So that's why I did this redefinition. So please don't murder me for that because it makes the computation possible. You take a first order condition off of this with respect to H. So I guess you can do that here. It's just going to be pH of 0. Oh no, this is negative because you're going to move this on the other side. So pH of 0 times u sub c of this base function is going to be equal to u sub h of this same utility function with nothing, with just a 1 outside. And the reason that this is positive here is because I just moved it over to the other side. So that should be fairly straightforward. You can take comparative statics on this, just like we did with the last one. We basically solved for the optimal level of housing, and then we took comparative statics with respect to distance. And you can show how pH of 0 and H star of 0 change with respect to a wage and an optimal level of reservation utility. But it's just sort of a pain to work with, and it's a rather messy functional form. So I'm going to choose a different one. So I'm going to close the model with H is equal to 1. So because we assume that consumers are homogeneous, we're going to assume that they're all going to assume a relatively equal amount of housing. And then we're going to end this presentation by going back through with this and letting H be flexible. So we have a U of KW minus a P0, pH of 0 of 1. And we let H equal 1. That's the case, basically. That's just your base utility function now. And I want to go back and show you what it was previously so you can compare. So this is going to be going to take this function here, and this is going to be 1. This is going to be 1. So you're just going to have a KW minus pH of 0, comma 1. So yes, that's going to be U bar. And then we're going to basically just going to say that C hat of U bar is going to be the particular value of C, where the utility function of C hat of U bar, comma 1 is going to equal your reservation utility. So then from that, you know that this thing in here, the KW minus pH of 0 is going to be equal to your C hat of U bar. And then you can just move that around. And then you know that for all, you have an equation pH of 0 is equal to KW minus C bar, but minus C hat of U bar. And then we know that for all D, pH of D is going to be equal to this equation where you're just going to put in the A of D back in there. And that gets you this housing price for all urbanites, or all city dwellers. And yes, so just insert that here, because if you remember, your price of agriculture, your price of land, which we solve for here, is going to be equal to this pH of D bar over this crap here. And then yes, so then you can basically just insert what we solve. We just solve for pH of D here. Then you can just insert that in here, and then multiply it by these two deltas, the various exponents. And then you can then invert this agricultural price. So this is going to be the price of agriculture for this given city. So this can be the agricultural value of the land, and this is going to basically enable you to solve for the city edge. So basically, it's going to enable you to solve for how far out the city is going to go before you're going to start having farmland. Because then it will be, eventually it's going to be more profitable to grow crops and to have people there, because of low amenity values in my case, or because of large or long commutes in the case of the AMM model. So I'm just going to invert this now in order to solve for the city's geographic size, and it's going to be simple inverse from like algebra 2 or something like that. So part 2. I'm just going to take this, I'm going to invert it. So I'm going to divide up by this component here. And then I'm going to multiply this whole thing by a delta minus 1 over delta to get this to equal 1 in the exponent. And then I have this expression here. And then I can just move over the C hat and then divide out by 1 over KW. And then I can just take the inverse of this to get D bar. And this is going to be your function for how big radially the city is, or the city size. And we can basically model this city in terms of a relatively simple, I mean, if you would call this simple, equation. So this is again going to assume that you're going to have people consuming the same amount of housing. And then we can actually solve for population size using that D bar. If you remember that, actually, wait a second, is this yeah, H is equal to 1. Yeah, lovely. So yes, we can assume that this is just going to be 1 over H, or 1 over the land. If we essentially assume that H is equal to L, in this case, you can get the density function. So this is sort of the idea of everyone's living in like cheap tents. So basically, I'm just going to take this idea of solving for H and housing supply here. We solve for H is equal to pH of D over delta times 1 over delta minus 1. I'm just going to sort of invert that. If I did that correctly. No, I'm sorry, it's gonna be the same thing. Yeah, it's gonna be the same thing. All right, so never mind what I just said. So the density function is going to be straight up equal to the amount of land that everyone consumes, or to the housing supply, and you can just plug that in for that. So we'll move on from now. Basically, you can just sub this in. So you're going to sub in the pH of D, which we just solved for back in the previous slide. And then you just integrate this times the 2 pi j with respect from 0 to the optimal value distance we just solved for. And this is going to get you your population for monocentric city. So you're essentially just going to multiply by that 2 pi j because it's basically a circle. So that's the first part. This would be the case if housing is fixed among all consumers, and then now you have to assume it's flexible. So for this, I'm going to use a quasi-linear utility function in consumption, at least. What does quasi-linear mean? It essentially means that essentially, if you change or if you increase one component of the utility function, or in this case, it'd be consumption, you're not going to change the slope of the indifference curves. So it's essentially going to give you parallel indifference curves, at least in the 2 variable case or in the 2 good case. In this case, I'm going to just assume that B is exogenous. And I'm going to assume that this KAD thing that I defined earlier is going to be equal to a K times a 1 minus alpha D, where alpha is going to be some value between 0 and 1, and 1 minus alpha D is going to be positive. This again is so I can get any function out of this equation, any other function besides just a pH of D out of this thing. So I now have my utility function. I'm going to have the consumption, which is going to be this K times 1 minus alpha D times W minus pH of D times H plus beta ln of H. I'm going to take the first order conditions with respect to D and H. Essentially, I'm trying to try to set up a separable ordinary differential equation. So it's very simple first order conditions. It's just going to be negative K alpha W minus pH comma D H is equal to 0. From this, I can just semi-equal to one another. pH comma D times alpha H is going to be equal to negative K alpha W. If I differentiate this thing in respect to H, I'm going to have a PhD plus B over H equals 0. It's going to be a PhD is equal to beta over H. And then that's going to be the same thing as just multiplying the H on both sides, dividing up a PhD, and then you have a separable differentiation, a separable ODE here, which is probably one of the most simplest ones you could possibly imagine. I'm just plugging in the beta over the pH of D in for H here. So I have a pH prime of D over pH of D minus a K alpha W over beta. And I get that beta just from moving this beta here over to the other side. And this is going to be the separable ODE where you're going to have that some dP over P is equal to K, some K dt, right? Integrate both sides here. I'm going to have this is going to be the natural log of P. It's going to be equal to KT plus some constant plus C. And that's going to simplify down to, if I exponentiate both sides, P is equal to A e to the KT. So my solution is going to be basically pH of D here is going to be equal to pH of 0, which is basically my initial value, to the power of e to the minus KAW D over B, where D is like my T in this case. And because that pH of D is equal to the beta over H, I can just use this expression here and use that to get the optimal H value just by plugging in accordingly. And with that, because it's in the denominator, you're going to have this exponent become positive rather than negative. That just tells you that, again, you should have falling housing. I'm sorry, that as you increase the distance away from the city center, people should be consuming more housing if housing is flexible. So yes. Okay, so now we have this thing, part 2. So if you let D is equal to 0, this thing is going to be equal to 0 here. So you're just going to be left with the KW minus pH of 0 H of 0 plus beta ln of H of 0 is equal to some U bar. Remember that these things are all Hicksians. Also, probably note just a brief thing on Hicksian demand curves is that Hicksians are going to be called basically compensated demand curves, and that basically means that because of the dual problem you have in consumer maximization, where essentially if you're looking at a Marshallian, you're essentially trying to maximize your utility respect to some budget constraint. Whereas the other problem is that you're trying to minimize your expenditure, relative to you being able to retain some given reservation level of utility. The Hicksian is going to be sort of corresponding to the second instance of that. It's also developed by Sir John Hicks, who was an economist at the London School of Economics as well as Oxford. And anyways, it's called compensated because in order for a consumer to maintain the same indifference curve, if a price of a given good goes up, you'd have to compensate them somehow with some sort of additional income to maintain that given U bar. Whereas, the Marshallian demand curve doesn't work that way, so they would be called uncompensated instead. So anyways, going back to this thing, we're going to say that with d is equal to 0, you have this equation here, which is just explained. We know that h of 0 is going to be beta over pH of 0 from our last slide. So I'm just going to plug that in here, and then I can get the pH of 0 to basically cancel out. And then I can just get this expression kW minus beta plus beta times ln over beta over pH of 0 is equal to U bar. Then I can just rearrange by moving some of this over the other side and dividing by the beta. You get an ln of beta over pH of 0, exponentiate both sides. And then you have this expression here, which is going to be synonymous with pH of 0 is going to be beta times e to the negative beta plus kW minus U bar over beta. And again, just to explain the algebra here, to explain the algebraic part of this, I'm just going to basically move this pH of 0 on the other side, divide by this exponential function. And this exponent here is going to become negative because this is going to end up being in the denominator. So hence we have solved for the urban edge in this flexible housing model, where PA is going to be equal to pH of D equal to the pH of 0 times e to the k alpha W over beta times D bar. And it's going to be equal to this expression that we solve for because we know the value of pH of 0 that we just solved for there. So now we're going to plug that in here, and then you're going to see that you can just write this times this as this, and then we're almost done. You can then basically use this equation here to solve for the optimal distance, or just to solve for the distance of the city, because you know that the agricultural value of the land. And you're just going to do that by doing some brief division and taking natural logs. And then you can just go through the stuff on the slide, and then you can get this D bar value. And then if we assume that density is going to be proportional to 1 over H, or 1 over housing size, you can just integrate this whole thing here. Or I'm sorry, where is it? Just integrate the 1 over the housing value, which we should have solved for here. So 1 over this is going to be pH of 0 over beta times e to the negative k alpha WD over beta times 2 pi j, and dj from 0 to this optimal distance value. And therefore, you have closed the model. So that is an example of an urban model. As you can see, I modified it somewhat. I don't know if I'd say significantly. You have rather similar ideas that are being presented here in comparison to the original Bonds-Muth-Mills model. I probably could have explained the intuition better. I apologize. I spent like 20 hours on this as it is. So I hope you enjoyed it. It was a pleasure creating this. And it was a, sort of a fun little project. And I guess we should probably discuss very, very briefly, what the possible drawbacks could be for this. And the obvious drawback is that this is only going to work if you have a monocentric city where you're going to have amenities that are going to be, decreasing from the city's amenity values that are going to be decreasing from the city center. If you have batches, where you have a beach on some place, or you have multiple work centers, or really work centers don't even matter here. Although probably, yeah. So, you have different values for amenities. This isn't going to work as well. But this is just sort of a brief introduction for an urban model. If you want to look at this more, Ed Glazier did a presentation actually on specifically urban models that themselves, the Alonzo Muth-Mills model, and the Rosen-Rosenbach model. As a lecturer for the Urban Economics Association, and there's many other lectures, some even done by people at LSE, particularly dealing with like environment, I want to say. But anyway, this is just sort of an example of how you can use economic ideas to model things that aren't, things other than cost curves and budget constraints, and of course, well, we did some of that, but this is more so an instance of economic geography rather than what you think of by producing an optimal value or optimal number of widgets. So I hope you enjoyed. I apologize about the length, and I think that's going to be it for now. So thank you.